In exercise, we are going to start with the first problem. Find all positive integers when divided by 3. When divided by 3 in the sense the b value is given as 3 and leaves remainder 2. So r value is also given as 2. So what will we do is, we will consider the Euclid's division lemma a equals to bq plus r. A value is not known, which is we are asked to find, and b value is 3, q value is also not known, plus r value it is given as 2. So they are asked to find all positive integers. What does mean by positive integers? Positive integers starts with 0, 1, 2, it goes on, etc. So what we have to do is, we have to vary the values of q like 0, 1, 2, 3, etc. So first if I take the value of q as 0, I will get a equals to 3 into 0 plus 2. So a equals to 2. They are asked to find the all positive integers. First we got it as 2 while choosing the first integer as 0. Next if I choose q is equals to 1, what will I get? A equals to 3 into 1 plus 2. So a equals to 3 plus 2, a equals to 5. So the next positive integer is 5. If I choose q equals to 2, what will I get? Again I have to substitute the value of q as 2 in this equation. A equals to 3 into 2 plus 2. A equals to 3 2s are 6 plus 2. A equals to 8. So this is how we find the all positive integers when it is divided by 3 and leaves the remainder 2. This is the solution. Second problem is, a man has 532 flower pots. He wants to arrange them in a row such that each row contains 21 flower pots. So 532 is nothing but the value of A, that is divided, and 21 is nothing but the value of B, which is a divisor. We have to find the number of completed rows and the how many flower pots are left over. That is, we have to find the values of Q and R. First I will do it with the normal division. So 532 divided by 21. Let me choose 21 into 2. 2 times 2, 4. 42, 1, 1, 2. I will choose 21 into 5. 5, 10. So 5 times 105. 12 times, which is 7. So by the normal division we got the value of quotient as 25 and remainder as 7. This is the answer anyways. We are going to express this in a Euclid's division lemma a equals to bq plus r. This problem we are going to solve as we did the example 2.1. So which means total flower pots 532. So which is the dividend A, which is equals to each row contains 21 flower pots. This is the value of a divisor and it is expressed as B into what is asked to find? Number of completed rows. Number of completed rows. That is 25, which is a quotient Q, plus flower pots left over. Leftover flower pots 7, which we express as a R remainder. So Euclid's division lemma is A equals to BQ plus R. A value 532, B value 21, Q value we got it as 25 plus R value is 7. So in the third problem, what we are asked to do is, we have to prove that product of two consecutive positive integers is divisible by 2. Product of two consecutive positive integers. Positive integers means we can take only after 0 and Consecutive in the sense the next number. For example, 3 and 4 are consecutive numbers. 3, the next number is 4. So likewise, product of two consecutive numbers is always divisible by 2. This is an easy proof to do. What we are going to do is, we are going to prove this in two cases. First case, we will prove it for an even integer, and in the second case, we will prove it for an odd integer. In the first case, I am going to consider n as an even integer. Okay. So according to the given question, if it is a consecutive positive integer, means if n is the integer and the consecutive, the next number will be n plus 1. So already we have mentioned here n is an even integer. So n into n plus 1 in the sense it is consecutive integers, as well as this is an even number and this is an odd number, because we have considered n as an even number. Obviously n plus 1 means, for example, if n is 2 means it is an even number. 2 plus 1 will give us an odd number. So in that sense also it makes sense. N into n plus 1 divided by 2. That is what we have to check. Two consecutive positive integers is divisible by 2. This will definitely divisible by 2 because here we have considered n as an even integer. Any even integer will be divisible by 2. So n will be divided by 2. N into n plus 1 is divisible by 2. That is product of two consecutive numbers when n is an even integer is divisible by 2. Next, what we are going to do is, case 2, we are going to consider n as an odd integer. What does it mean? If n is an odd integer, then n plus 1 will be an even integer, right? Because n, if it is 3, it is an odd integer, then 3 plus 1 will definitely give me an even integer. And also these two are, if 3 and 4, it is a consecutive positive integers. We should check whether this is also divisible by 2. It will be definitely divisible by 2. Why? N plus 1 is an even integer. Even integer obviously will be divided by 2. Therefore, n into n plus 1 is divisible by 2 when n is an odd integer. So in both the cases, that is, for product of two consecutive positive integers, we have checked in both even and as well as in odd integer. Both even integer and the odd integer is divisible by 2. The statement is hence proved. So the next problem is, when the positive integers a, b, c are divided by 13, that is a divided by 13, b divided by 13, c divided by 13. When a is divided by 13, it leaves the remainder 9. When b is divided by 13, it leaves the remainder 7. And when c is divided by 13, it leaves the remainder 10. What we have to show that it is a plus b plus c which is divisible by 13. Let us do this. So first what will we do is, Euclid's division lemma, a equals to bq plus r. I will consider this as an equation 1. So first a is divided by 13. A is a dividend, 13 is a divisor, q plus remainder is 9. This I will consider as equation 2. Next b is a dividend, 13 is a divisor, it leaves the remainder 7. Next c is the dividend, 13 is the divisor, leaves the remainder 10. This I will consider it as equation 3, this I will consider it as equation 4. Now what we have to do is, we have constructed the equations according to the given problem. Now we have to show a plus b plus c is divisible by 13. Let us do so. A plus b plus c in the sense, equation adding 2, 3 and 4. So left hand side will become a plus b plus c, which is equals to 13q plus 9, 13q plus 7, 13q plus 10. So a plus b plus c, which is equals to 13q, 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 3 times it will become 39q plus 19, 19 plus 7 it will give us 26. So if I take 13 in common from this, a plus b plus c equals to 13, I am taking it in common, 3q plus 2. So on the right hand side, if you see, we got the value as 13 into 3q plus 2. This number will be divisible by obviously 13 because it is getting cancelled. So what we got is the right answer. Hence proved. Therefore, a plus b plus c is divisible by 13. Prove that square of any integer leaves the remainder either 0 or 1 when divided by 4. So, what is given is square of an integer, any integer, if it divides, it gives only the remainder 0 or 1. But they haven't mentioned it is an even integer or an odd integer. So, we will check for both the cases. First, what will we do is, first we will consider an even integer. X is equals to 2n, because 2n means multiples of 2 will give us an even number. That's why I am considering x is equals to 2n. Square of any integer. Square of any integer means we have to square it on both the sides. X square is equals to 4n square. This x square is nothing but our dividend. This 4 is our divisor. N square is our remainder. Plus remainder we didn't get anything, which is 0. That is, this is proved because square of any integer leaves the remainder either 0 or 1. We have taken an even integer and it leaves the remainder 0. What it is mentioned is it should leave a remainder either 0 or 1. It has left the remainder as 0. Next, similarly, we will do it for an odd integer. This portion what we are going to now do is, we already did it in the example problem as well. Consider an odd integer. Okay, x is equals to 2n plus 1. Why 2n plus 1 is 2 into n, multiples of 2 represents an even integer. So 2n plus 1 will obviously represent an odd integer. So x is equals to 2n plus 1. According to the proof, square of any integer. Therefore, we have to square it on both sides. X square is equals to 2n plus 1 whole square. X square is equals to, on the right hand side, we are going to expand it using the a plus b whole square formula. A plus b whole square is equals to a square plus 2ab plus b square. A value is 2n and b value is 1. Let us directly substitute. A square is 2n square, 4n square plus 2 into a into b. 2 2s are 4n plus 1 square is 1. Let me take 4n common from the first two terms. X square is equals to 4n into n plus 1 plus 1. This n into n plus 1 I will consider it as a q. X square is equals to 4q plus 1. So now if you see, a is the dividend and 4 is the divisor, q is the quotient plus 1 is the remainder. According to the proof, square of any integer leaves the remainder either 0 or 1. When we took an odd integer, it left us with the remainder 1. Therefore, proof, hence proved.